talking about how boats float. The science behind floating was first discovered by an ancient Greek scientist named Archimedes. He figured out that when an object is placed in water, it pushes enough water out of the way to make room for itself. This is called displacement. All of you have also experienced displacement, like when you get in a bathtub and the water falls over the edge. When an object enters water, two forces act upon it, as we can see in this nice diagram. The first force is gravity, which is the downward force. And the second force is buoyancy, which is the upward force. Archimedes' principle is that buoyant force equals the weight of displaced liquid. A boat will float if the gravitational force is less than the buoyant force. In other words, boats will float if it weighs less than the amount of water it displaces. For example, a rock will sink because it displaces only a little bit of water and its weight is greater than the weight of the amount of water it displaces.
So now we're going to do an example of what we just discussed. Here is an empty cup, and when we put it in the water, it floats. So say we pour some coins into the cup. Now when we put it into the water, so because this is full of coins, it weighs more than the amount of water that it displaces, so it sinks.
Yeah. Come on in here, class, and learn about how and why the boats float with a handy-dandy example and equation. So, for now we have an example, like a word problem, that I'm going to read to you guys. So it starts with, empty canoe is floating by a dock in a lake. The bottom of the canoe has a surface area of 2.70 meters squared, with nothing in it. The canoe displaces only 2.00 centimeters or 0.0020 meters of water. Then the canoe is filled up with gear for a camping trip. Once the canoe is fully loaded, it displaces 30.0 centimeters or 0.300 meters of water. How much more buoyant force is exerted on the canoe by the water when it is fully loaded versus when it is empty? Let's dive right into this problem, folks, starting with the force of buoyancy equation, which is force of buoyancy empty because the canoe was empty at first, P times G times height, that's empty, times capital A. P stands for the density of the liquid, G stands for the gravitational acceleration, which is 9.8 meters per second squared, which is always given to us. H equals the height of the water displaced by a floating object, which is meters. And capital A is the surface area of a floating object, meters squared. So if we get to writing, equals 1,000 times 9.8, which is given to us, times the height, 0.020 meters, times capital A, which is 2.70, and what we'll get from that is a handy-dandy 52.92, and so that's our F empty. Now we're moving on to F loaded, which is the same thing as the equation above, just instead of using the numbers from when the canoe was empty, we're going to use the numbers from when the canoe was filled with the gear. And that equals the same, so it's the same equation, so we're going to do equals 1,000 again, times 9.8, times 0.300 meters, then times 2.70. And then the answer for that is we get 7,938 kilograms times meters per second squared, which can turn into a 7,938 newtons. Ahoy, mateys! I know you got a little seasick on that last part of the problem, but don't you worry, we're nearing shore and to the end of this video. So the next second equation we're going to be using is delta F equals F loaded minus F empty, and delta F stands for the difference in the forces, which will give you the overall buoyancy force of this of the canoe. So delta F equals 7,938 newtons minus 52.92 newtons, which gives you delta F of 7,885.08 newtons. But don't forget sig figs. So just round it to 7,885 newtons is our final answer. Yay!
Thanks for watching, everybody. Stay afloat.
You got a fast car. I wanna take it to anywhere. Maybe we'll make a deal. Maybe together we can go somewhere. Any place is better. Starting from zero, got nothing to lose. Maybe we'll make something. Me, myself, I got nothing to prove. You got a fast car.